Okay, welcome to today's speaker in the ZMS seminar, Melissa Tacy from the University of Auckland, speaking on adapting analysis synthesis pairs to pseudo-differential operators. Thank you very much.
So thanks. I'm just going to tell you a bit today about some of the work I've been doing, which came out of trying to understand how joint eigenfunctions of some differential operators behave. I'm just going in and out of the view. For some reason, I'm having problems navigating my slides. There we go. So what I wanted to understand was solutions to P of U is equal to 0, where P is some differential operator, and I'm interested in these scaled differential operators. So what you've got here is you've got a sum over various derivatives. This will be a finite sum, but I don't really care about what order it is. We use a multi-index notation, which is a nice compressed way of saying how many derivatives in which variable we need to apply. You've got your coefficients, and your coefficients can depend on x. One little thing that might sort of stand out as a bit different than what a lot of people do is my differential operator has the 1 on I factor in it. And that's because I'm often using things related to the Fourier transform, and this kind of 1 on I makes a lot of the formulas involving Fourier transforms really nice and simple. So I want to look at these solutions, and I want to know about the concentration of the function that you get out. And the particular thing that I'm interested in is the LP norm. So I'm going to measure the LP norm. I want to compare it to the L2 norm, which I'll always normalize to 1. And so the questions are, so for which functions is that inequality true? And F will usually depend on H, N, and P. And of course, you want it to be a good F, right? It's actually pretty easy to find a F that works, but it gives you a terrible estimate that is never saturated. So what you're really aiming for here is actual saturation of your estimates, not just an estimate. So I'm going to put this in the setting of semiclassical pseudo-differential operators, which is just, it's a nice framework to see these sort of problems. So instead of working with a differential operator, I'm going to work with a pseudo-differential operator. I'm still solving this equation, P of U is equal to 0, where P is an operator that is given by this oscillatory integral. Now, if you're familiar with standard pseudo-differential operators, this should look very much like the formula from those. The only difference is you've got this H factor in here and a normalization, which keeps everything nice in L2. If you're not familiar with pseudo-differential operators, you can think about this. If P only depended on xi, then this operator is take the Fourier transform, multiply by P, and take the inverse Fourier transform. So it would be a multiplier. So you can think about this as a multiplier that is sort of allowed to depend on x a bit. Now, Pxi, we call the symbol of the operator, and the transformation is that multiplication in the symbol goes to differentiation in the operator. So it's this Fourier transform association. So if I had my differential operator, then it goes multiplication times xi alpha to transforms into my original operator. And I have these factors of H throughout. So the factors of H, you want to build them into the operator, and H will be a scale parameter. It'll be a small value that has some kind of significance in your problem. So if you do it, it's called semiclassical because it came out of quantum theory, and in that case, H is sort of related to the Planck scale or the energy of the system, but it could be other things. So H you should think of as some kind of important parameter in the problem. Now, almost everything that I do is what I call local. And locality has a bit of a difficulty in this case, because ideally what you want to localize is in position and momentum. And of course, the uncertainty principle tells you you cannot perfectly do that. So what you do instead is you define one of these operators where you take a function that is supported compactly in both x0 and xi0, and you create an operator out of it. And so this operator doesn't completely cut off the function or completely cut off its Fourier transform, but it gets the closest thing that you can do given the constraints of the uncertainty principle. Okay, so it allows you to do the best you can. And then because of the small support of the function, you can work reasonably locally. Now, the advantage of this is you can feed this all into the semiclassical calculus, and it tells me that if I apply P to this localized version of U, that's the same as localizing, then applying P plus an error, which has an extra power of H. Now, remember, I said H is small. So the idea is that this error is not so bad. Introducing it is not so much of a problem. So instead of looking at solutions that exactly solve P of U is equal to 0, what we actually do is look at solutions that approximately solve it, because whatever we do, we're going to get this error from our localization. So we may as well not start with an exact solution anyway, because in our first step, we're going to be turning it into an approximate solution. So we're going to measure everything in terms of the error. And the error we define is we apply P to U, we measure its L2 mass, and we compare that to the L2 mass of U itself. And so the idea is that if this is small, then U is an approximate solution, or what we call a quasimode, a reasonably good solution. So come to one of the big ideas of this talk. And so this is the idea of Fourier integral operators. And I've sort of picked up this and put it in inverted commas, the algorithm of the 70s. So this isn't what I said. This is what Pfefferman said. I don't know what else they were doing in the 70s, but apparently this was the algorithm, not just an algorithm. So what it is we're trying to solve an equation P of U is equal to 0, or P of U is small if we're dealing with a quasimode. Now, firstly, if the symbol is not 0, then we've got this calculus that tells us we can invert. So you should think of this as being an idea that if the symbol is not 0, the operator is invertible, right? Symbol is invertible implies operator is invertible. And so that's a sort of a nice rule of thumb that we use. So if this is non-zero, then we can invert, and the only solution is U is equal to small, or U is equal to 0. So that tells us what we're actually concerned with is things localized near the set where the symbol is 0. And this is where the algorithm of the 70s comes in. The idea is we're going to convert our complicated semiclassical pseudodifferential operator into a simple constant coefficient differential operator. In fact, one that is really, really easy. So it says, well, here is my 0 set, Pxi is equal to 0. Okay, it sits in phase space, so 2n dimensional. Now, if I was just dealing with a function, I could define a change of variables which flatten that surface out to become xi1 is equal to 0. Now, xi1 is equal to 0 is associated with the operator h dx1 is equal to 0. So the x1 derivative is small. Okay, now that's a nice, very simple ODE, PDE that we can solve very explicitly. So what the algorithm says is, say we come up with a map, W, which quantizes this behavior. Okay, so which really does achieve what we want to achieve. It takes solutions to P of U is equal to 0 to solutions h dx1 of V is equal to 0. And obviously we need that to have an inverse, because it's of no use to us if we can create a new simple thing and solve it, and we can't invert it to come back to our original. So the algorithm of the 70s is this idea that we're going to take a complicated PDE and convert into a simple one. So what do we need? We need an operator W, which has the property that h dx1 of W is W of P. And so if we have an approximate solution u of p of u is 0, then we set v is equal to w of u, then v is an approximate solution to h dx1 is equal to 0. So we're going to try and solve for v. Now, if it was an exact solution, p of u is 0, then v would be an exact solution. But we almost never have exact solutions. So when I say an approximate solution, the first thing I want to know is how good of a solution it is. If I know how good a solution u is to pu equals 0, how good a solution is v to the constant coefficient equation? Then I obviously want to know about producing an inverse w to recover u from v, because the whole process, really needs that. Then finally, how are the properties of v related to the properties of u? So I might solve for v, get a very nice expression for it. How do I pull that across to get some information about u? So in the 70s, a lot of the L2 theory was worked out, and the L2 theory is very nice. So in the case that you're locally a graph, you can produce a unitary operator w that does this. So what this means is, yes, we can get inverse. And if u is a quasimode of a certain order for p, then v is a quasimode of the same order for the hdx1 operator. So the operator w preserves the error as well. And then because it's unitary, this then tells us that the L2 theory is the same for u and v. So then they had a real payday in the 70s where they went through and extracted a lot of existence, uniqueness, and properties from this when you're working in L2. But I want to look at the LP theory, and I know off the bat it can't be the same. So it cannot be the case that you can just transfer the LP theory across. And there's a very specific example that you can look at to show that. So I'm going to consider two operators. Pxi is xi1 minus xi dash squared. And then the set xi1 is equal to 0. So that's say P2 is xi1. So this xi1 is equal to 0 is a nice flat set here. But the set where xi1 minus xi dash squared is curved, and this curvature matters. So if I take order h quasimode, what this means is that if I look at the Fourier transform of this thing, because it's constant coefficient, so I can just Fourier transform. If the solution is order h, the Fourier transform, if you multiply it by p, has to be also order h. So I can make my solution live in this little blue fuzzy region. And of course, the reason why it's fuzzy is the uncertainty principle. I can't put it absolutely perfectly on the hypersurface and still make it a function.
Sorry, I could just interrupt with a question. I lost the thread here. C1 is basically ddx1. What is C prime?
Z prime is the other direction. So, z1 through xen.
Oh, okay.
Then, all of them, they just get rolled together.
Okay.
And I've drawn it in sort of 2 dimensions, but you're imagining the other dimensions are sort of just there hanging in the background. So I can look at the LP for this, and to get the sort of the maximal LP growth, what I do is I try and spread out my Fourier transform as much as possible. Now this comes in from an uncertainty principle idea that if I want to concentrate the function, I should spread out its Fourier transform. So I want to concentrate this as much as possible, close to one point. I'd better spread the Fourier transform as much as I'm allowed to do so. And in that case, I can find examples where I have a growth rate where the LP norm grows as h to the minus n minus 1 on 2 plus n minus 1 on p. So it's L2 normalized, but it has quite sharp growth in the other p values. So p is always greater than 2 in this case. However, this thing here, this is a curved surface, so it falls into the sort of the realm of the restriction extension conjecture. And although that still remains a conjectured result, already partial results imply, say, like Thomas Stein, imply better estimates than for the flat surface. And there is, there's quite a theory around the fact that curved surfaces have lower LP growth. So we know that we're not going to get a relationship like we got for L2. We know that there's going to be a difference between the LP behavior of V and the LP behavior of U. And all of that is contained in the structure of the operator W. So that's what we really need to get our hands on and understand to be able to extract the LP information. So I'm going to jump a little bit to looking at analysis synthesis and then come back to how that is used with the operator. So analysis synthesis, this is something that is very common in harmonic analysis. So the idea is that you want to analyze a function by breaking it up into simple functions. Okay, and the form of the simple functions depends on your situation and many, many different decompositions you can do. So I'm just going to write this out in the most general way I can. So I've got a parameter space lambda and an analyzing function phi lambda. My analysis operator takes V and takes its inner product with phi lambda. So this is the L2 inner product. I integrate V against phi lambda, and I'm sort of saying how much like phi lambda is V. And if this is a good system, I have a synthesis which says V of X is given by an integral of my coefficients here, which I got from my operator, times the synthesizing functions, and then there's some suitable measure. So we'll move into the more concrete ones that I'm interested in. So the first one is a semi-classical analysis. So this is very much like the standard Fourier analysis. It just has this factor of H through everything. So my parameter space is Rn, and my analysis parameter is xi. My analysis function is the plane wave in direction xi. So if this were the standard Fourier transform, this would be the same as setting H is equal to 1. But I want to get that scale in here. Okay, T xi V is sort of secretly the Fourier transform. It's the inner product of V and phi xi. And the Fourier transform, of course, has an inverse. So I can synthesize V in terms of its Fourier coefficients. The other one that I want to use is a wavelet analysis. And so here we're just looking at one dimension. And my parameter space is R2. I have two parameters A and B. And they tell me with my wavelet about dilation and displacement. So A tells me about how I dilate. So I have my function F, which has integral 0, and A tells me whether I compress or stretch it out. And then B tells me about how I move my function around the real line. The analysis is the inner product of V against phi, and then the synthesis for the continuous wave wavelet analysis is given with a measure dA/dB on A squared. So those are the two analyses that I will be using as we go forth. All right, so now I want to combine this with the FIO. So suppose I have E of P U is equal to 0 or H, and I do my transformation so that I'm now across to satisfying my constant coefficient equation. Now, all of these analysis synthesis, these tend to come out from harmonic analysis from the constant coefficient case. You know, wavelets and Fourier transforms are at their strongest in the constant coefficient cases. And I've taken my complicated non-constant coefficient, maybe even non-differential operator, and produced a differential constant coefficient thing. So this is a good one to do an analysis synthesis with some of these classical things like Fourier or wavelet. So the idea here is I will synthesize V in terms of some phi lambda, then apply W inverse to get back to U, and assuming everything in my integral is nice, I can pull the W inverse through and apply it to phi lambda. So what you should be thinking about this is now phi lambda was my original analysis synthesis. Then I get a new analysis synthesis where the analysis functions are given by W inverse applied to phi lambda. And so this is what I mean when I say that it's adapted to P. It's adapted because if you choose an analysis synthesis that works really nicely with HDX1 is equal to 0, then your new analysis synthesis is going to work really nicely with P of U is equal to 0. So you're using this to build a new analysis synthesis that sort of matches your operator. And I want to apply this to the study of joint Quasimodes. So the idea of joint Quasimodes is, say you have a function U that obeys, say it's a Laplacian eigenfunction, and you have some other equation like a momentum operator or a symmetry operator or some other differential equation that it satisfies. So that's when I would say that it is a joint solution. So it has more than one operator that it obeys P of U is equal to 0 for. For Quasimodes, what this is if I apply P1 to the M1, P2 to the M2, I get a power of H for each application that I do of one of these operators. It doesn't matter what order I do them either. And then you want to look at the two sets where the functions are 0. So again, this comes down to the idea that if one of these was non-zero, I could invert it. And if I've got, say, P1 of U is 0 and P1 is invertible, then U is 0. If I've got P2 of U is 0 and P2 is invertible, then U is 0. So I need to actually look at where both of the sets are 0. So that's where the contact matters. So I'm going to have these two sets and I'm going to specialize to 2 dimensions. So these are hypersurface in 2 dimensions, therefore they're curves. And you can characterize the way curves meet by measuring their contact. So they have a contact point. It meets with order K contact. Question is, how large can ULP be? Now, if K is 0, I have some earlier work that shows that the LP norms are uniformly bounded by the L2 norms. And that's the strongest result that you could ever have. Okay, that the LP norms just cannot grow at all. What I want to ask about now is higher order contact. And what I usually do is, before I would go and try and do the general case, is I'd bring it back to a constant coefficient model and use the Fourier transform to try and get an idea on what I might expect. So here's my constant coefficient model. I'm going to P1 be mod xi squared minus 1. So this is the symbol that's associated with Laplacian eigenfunctions. And these Laplacian eigenfunctions, because they show up so often, are quite often what we're interested in. P2 is just an operator that I've cooked up, so it will have second order contact at 1, 0 and be constant coefficient, so that I can solve this with the Fourier transform method. Now, if I take a Fourier transform of a function V, my semiclassical Fourier transform, I have the relationship that H times differentiation goes to multiplication. So it's pretty much the same thing that you'd be familiar with for the standard Fourier transform. There's just this factor of H running around. This prefactor being H to the n on 2, this means that you have the isometry property of Fourier transforms. So with this prefactor, the semiclassical Fourier transform preserves L2 norms. So what this means is if I have a constant coefficient pi of h dv is L2 order h, I Fourier transform that to a function where I have p, which is a multiplier, times the Fourier transform is order h. So I've now got an algebraic thing that I'm going to solve on the Fourier side, or at least approximately solve. So I've got to find out what the zero sets are, and I've got to make sure the Fourier transform of V lives within sort of size h of both sets. So if we have a look at this, here's my point of contact. Now, if I want to remain between, so the black line is P1, the blue line is P2. If I want to remain within order h of both of them, where do I have to be? Well, firstly, I must be on the h annulus around mod xi is equal to 1, because I've got this solution that says mod xi squared minus 1 is small. So that's my first condition, is I live on an annulus around here. My second condition is that I have to live on a little h region around the blue curve as well. And now up here, once I get xi2 being too large, I can't simultaneously be within h of both surfaces. So then this tells me that in fact, I have to keep xi2 smaller than h the 1 on k plus 1 if I want to solve both simultaneously. So that's a restriction that will apply to any of my solutions. And I'm going to analyze what possible growth rates I could have by constructing a family of examples that have different kinds of spread on the annulus, and then working out which examples could be joint Quasimodes and which ones could not. So I'll have chi alpha, which is equal to 1 on the little h annulus. So this is always a Quasimode for the first operator. And I will further restrict xi2 to be less than h the alpha. Otherwise, it's equal to 0. So this is essentially going to be my Fourier transform of V. But I need to normalize it, okay, because I want to keep everything L2 mass 1. So if you work out what the correct factor is, I need to multiply it by h the minus 1 plus alpha on 2. So now my example, T alpha of x, is going to be the inverse Fourier transform of chi alpha times the prefactor. And so what I want to see is how big are the T alpha and in what regions. So here's the formula for T alpha in 2 dimensions. So I've got my prefactor there, the 2 pi on h, that just comes out of the definition of the Fourier transform. And then I have my oscillatory integral. Now I'm localizing everything near the point 1, 0. So the idea is that this is something that its oscillation is going to be very much like e to the I x1 on h. So I pull that factor outside of the integral, and now I'm going to be integrating an oscillatory function with this phase, x1 xi1 minus 1 plus x2 xi2. And so my idea is that I want to know, when does this oscillatory factor not differ from 1 very much, right? If x1 and x2 are 0, then this is e to the 0, so it's equal to 1. So if x1 and x2 are very small, this thing will be approximately equal to 1, and then I can just treat it like it's 1, and the integral is really easy to do. So I need to work out, what I can, how big I can make x1 and x2. So xi2 is smaller than h the alpha. So therefore I get x2, if I make it less than epsilon h to the 1 minus alpha, then the product of the two will be less than order h. And so I won't get to do 1 cycle of my periodic function. I'm on the circle, xi1 equals 1, the square root of 1 minus xi2 squared. So if I do a Taylor expansion of that, I find that if x1 is less than h to the 1 minus 2 alpha, then xi1 minus 1 has to be less than h to the 2 alpha. So that also doesn't give me any oscillation. So now I've got this little blue region, and in that region, I can treat the oscillatory factor in the integral as if it was 1. Now, it's important T alpha of x is not 0 off the blue region. Okay, it's something else there, and we don't really want to worry too much about what it is. We just want to focus on this blue region. So if I focus on the blue region, I treat that like it's 1, I get that T alpha on the blue region is greater than h to the minus a half plus alpha on 2. And then, of course, I can compute what the LP norm on the blue region is, right? It has at least this growth, and that gives me some kind of example for whatever estimate I get could not be any better than what I get for these examples, right? Because they exist, so they immediately give me some kind of necessary conditions on what kinds of functions might work in the inequality. Okay, so some possibilities. To be a quasimode of P2, I need that alpha is greater than 1 on k plus 1. I'm looking at contact higher than 1. So alpha is equal to a half is always a possibility for every value of k. And if you run through the numerology there, this alpha is equal to a half example, this controls the low p estimates. So in fact, when p is smaller than 6, you're going to get no improvement from assuming that you're a joint quasimode. You get the same estimate as you would for just assuming you're a quasimode of the original Laplacian type operator. However, for high values of p, it does start to rule out some possibilities. And so for high values of p, you use this uncertainty principle again, and you say, I want to make it as big as possible in one small point. So I want to spread the Fourier transform as much as I can. Now I can only spread it up until alpha k is equal to 1 on k plus 1. And here is the numerology for that. So then you take a leap of faith and you say, all right, I've got these two examples, one of which is sort of one end of the family. The other is sort of the other end of the family. And I would expect that everything else in the family would be better than these two, or at least the same. And so you conjecture that these estimates are what you would see in the general case. And you find out that that is in fact correct. So if you have a strong joint order H quasimode, so this is just assuming that you can apply P1 and P2 as many times as you want. You have the two sets meet with order K, and this first set is curved. That comes back to what I was saying before with the fact that curved and flat sets are different. Then your worst growth is for P between 2 and 6, it's given by minus a quarter plus 1 on 2P. And from P6 to infinity, it's given by this function that depends on the contact order. And we know this is sharp because we already have the examples that is sharp. And it follows just from a combination of Fourier integral operators with the analysis synthesis pairs. So I'm going to say I've got P1 of u is equal to 0, and I'm going to convert it to the equation h dx1 of v is equal to 0 by setting v is equal to w of u. And so now I want to do an analysis synthesis of v. And because it's a constant coefficient equation, there are lots of good options. The one I'm going to choose to do is wavelets. And the reason I'm choosing this is, say, over Fourier transform, is that it has locality. So a Fourier transform is a global thing. you're decomposing things into waves that are not localized at all, whereas wavelets have some localization built in, and that helps with the analysis. So I decompose V and write it in terms of its synthesis. Now, I'm only doing this decomposition in X1. X2 is just fixed, okay, because I have no equation for it. From P1, all I get is that HDX1 of V is equal to 0. So you can see X1 is just at the moment, it's just along for the ride. But I do want to use that variable because I haven't used yet that I'm a joint quasimode. So I also know that U satisfies P2 of U is order L2 of H. So what I want to do is I want to transform my P2 across to this new setting, right? So I took my little blue line and I flattened it out with W. What does the black line become when I apply W to that? And what you find is that maybe you don't get a good equation for the black line, but what you find is that the order of contact is preserved. So if this two curves has contact order K over here, and I apply my map W to flatten out one of the curves, I preserve my order of contact. And in fact, I can show that V is a quasimode of HDX2 to the K plus 1 of V, and its order H. So now V satisfies two constant coefficient equations. And there are many decompositions I can do in the X2 variable. In this case, I choose to do a Fourier transform because I have this nice relationship that I knew the Fourier transform xi2 has to be within h to the 1 on k plus 1. So it's very useful to use the Fourier transform here because I already have some information about it. So what I mean here is that I'm taking the wavelet or in X1 and then the Fourier transform in X2. I place my cutoff and then I sort of feed this all into the Fourier integral operator and apply some pretty standard techniques. And once I do that, then I can verify that in fact the growth rates that I conjectured were true. And I'm not going to go into that in detail. What I'm going to do is talk about what I want to do next. So I said that wavelets are very good when you need some locality. So one of the things I want to do next is look at some examples where you might have better error in some regions than others. So maybe you have a point around which you're not really sure about how good your error is. It gets a bit worse around there. Wavelets are very good for that because they have locality, so you're not having to be globally good. You can break it up and have a look at what it is locally. There are other analysis synthesis pairs that you can use for different problems. They may be more appropriate. Typically, you choose your analysis synthesis to suit the problem. A big thing I want to look at is higher dimensions. The thing with higher dimensions is that contact becomes more complicated. So in 2 dimensions, you're dealing with these characteristic sets that are curved. If you want to talk about the contact of 2 curves, then you just talk about the order of the contact at the point that they meet. Now think in just in 3 dimensions and think about how you might classify how hypersurfaces meet, like 2-dimensional hypersurfaces meet in 3 dimensions. So immediately that's much more complicated. So there's quite a bit of a classification problem just to set up the higher dimension and things. And so that's why I only looked at the 2-dimensional case when I was looking at the contact condition, because the higher dimensional case has there are some really embedded things that are much, much more difficult there. And then for all of these, once you've got the linear estimates, you want to start looking at bilinear and multilinear estimates. And there are all kinds of things you can do in constant coefficient cases. and you want to might think about how you can use these techniques of Fourier integral operators to map across from your non-constant coefficient case to your constant coefficient case, to give you a sort of a more effective way to solve them. So I can't see the time to know whether I'm early or late or anything.
You're good. It's 3:43.
All right. Well, I will stop, I think, here and allow any more questions.
Okay, thank you very much, Melissa. Well, I'm not an analyst, so that seemed like an enormous field of study that you were mapping out there, because you seem to be dealing with extremely general class of problems. Are there any questions? Just speak up if you have one. So I guess my question is a little bit related to your first point on the slide here.
Mm-hmm.
Just because I have sometimes used wavelets, but that's like a specific set of wavelet basis functions. So is your point there that you will actually be constructing a specific set of functions and tools to do the transforms for a particular problem, or are you more thinking of a much more general class of problems?
So ideally what I'd like to get is sort of two things. One would be a really generalized sort of machine that tells you, if you have this sort of problem, this is the sort of, here are some analyzing functions that will be good for it. But also to look at sort of general classes. So in some sense, you want to match it to your problem, but you don't want to be, every time you do a new problem, you don't want to be creating completely new analysis synthesis. So what you might want is, say, here is an analysis synthesis that works really well if you've got a boundary. Here is one that works really well if you've got a corner. That kind of level of generality is what I'm aiming at.
It's pretty big. It's a very big problem and big topic you're mapping out. Okay.
Yeah.
Excellent. Okay. Any final comments from anyone? Okay. Well, thank you very much. And I am going to look up your recent papers to try and get some of the details behind your talk today.
Thanks.
If everybody could just now unmute your microphone, and we'll give Melissa a round of applause. Thank you. We can do on Zoom, I'm afraid, but and you don't get an afternoon tea either, so sort that out yourself. Thank you very much.
All right. See you.